Okay. So you guys got your little note thingies, and we're going to learn about Hooke's law. This guy named Robert Hooke, who is alive, a contemporary of Isaac Newton's, and he discovered what's true about springs. So we got Hooke's law, and Hooke's law, you know, is F equals negative kx. Now, I got to tell you, for the purposes of our class, you will never, ever, ever have that minus sign there. Whenever you use a spring force, you're always going to just use kx. You're not going to put negative kx. The reason I put negative kx here is just to emphasize something very important about springs, and that is springs always exert a restoring force. Let me show you what I'm talking about. Let's say I had a horizontal spring that looks like this. This is a relaxed spring. And then let's say I displaced it to the right. Okay? That is, I displaced it in that direction. My x is in that direction. Let's say I displaced it by pulling on it with my hand. Whoa. Thank you, Ezina. That way I don't have to bend down and get it. 1, 2, 3. Okay, so, thank you. So imagine I displaced it to the right with my hand. You tell me, what's the direction of the force that the spring is going to exert on my hand? To the left, right? Yeah, to the left. This spring is going to exert a force to the left because the spring wants to restore itself to its relaxed position. You understand that? That's the way we as human beings are. That's the way I am. When I'm sitting on the couch relaxing, my daughter or son or wife have some need that I have to satisfy. My goal is to satisfy that need as quickly as possible so I can get back to the relaxed position on the couch. Okay? Well, it's the same thing with a spring. And we call that it is exerting a restoring force because it wants to restore itself back to the relaxed position. Let's say instead of stretching the spring, let's say I compress the spring. Okay? So now my little hand is pushing on this spring. Okay? Let's just go like that. So what's happened is, oh shoot. What's happened is I've given a displacement to the left, and now that I've given a displacement to the left, the force that the spring is going to exert on my hand is going to be to the right. Again, the force always goes in the opposite direction of the displacement. But we have that minus sign there just to tell the world that. But the fact of the matter is, when you're working with F equals kx, you're never going to have a minus sign. You'll just use positive. Let's look more at this Hooke's law. Hooke went the opposite direction as us. We had our force in our lab yesterday. The force was the independent variable, and how much you stretch the spring was the dependent variable. But with Robert Hooke, he prefers to think of the stretch as being the independent variable and the force being the dependent variable. That is, he's going, hey, my hand is stretching or compressing the spring. How much force is my hand experiencing? So he just thinks about it a different way. And so this K, which is the spring constant, is going to have different units than the slope of the line that we got yesterday. You tell me, what's the units of Robert Hooke's spring constant? Say again? Yes, Fatima? Yeah, newtons per centimeter, right? Unless you're, who's one of the people who use meters? Okay, or if you're Ezina or Sean, then it'd be newtons per meter. And because there's ambiguity, you always have to make sure you tell me what the units of your spring constant is. Don't just say spring constant equals 12, because I won't know whether it's newtons per centimeter or newtons per meter. But you see, it's different from here. Here where you're saying, okay, I'm going to move 4 centimeters. I'm going to stretch 4 centimeters for every newton of force that I exert. But you tell me, let's say I told you I had a spring constant of 15 newtons per centimeter. What would that mean? Like, what does that physically mean? It doesn't mean I'm going to stretch 4 centimeters for every newton of force I exert. What does this mean?
You're going to exert 15 newtons for every centimeter?
Say again?
You're going to exert 15 newtons for every centimeter?
Yeah, you're going to exert 50 newtons for every centimeter of stretch that you want. If I want 1 centimeter of stretch, I got to exert 15 newtons. If I want 2 centimeters of stretch, I got to exert 30 newtons. You see what I mean? So it's a different way of thinking of it, but it's the same sort of thing. It ends up being the slope of the line. Okay, well, hey, then it is time for you guys to do example number 1. Please read example number 1 now on your sheet. I just destroyed a precious blue marker. Okay, great. Someone tell me, according to example 1, what's going to be my strategy? What do I have to do first? Yes, Alyssa? Yeah, solve for k, right? For example 1, okay, step 1 is to solve for k. Do f equals kx and solve for k. Once you solve for k, how are you going to answer the next question? What should I do now? Yes, Alyssa?
Use k to multiply by the distance to find force.
Thank you. Just use f equals kx twice. Yeah, so please, I'd like everyone to do that now. Use f equals kx to find k, and then use f equals kx to answer the question. Just like Alyssa told us to do. Wow. Mr. Shane. There we go. All right, you guys done? F equals kx. So I say that takes 20 newtons to stretch this guy 10 centimeters. So I get 2 newtons per centimeters equals k. How many people got that? Hey, yay. By the way, did anyone use meters? Did anyone call it point? Okay, good. So what'd you get as your k?
I got 200.
Beautiful, beautiful. If you got 200 newtons per meter, hey, that's the same darn thing, and that works out just fine. Alrighty, so now let's go ahead and do this. F equals 2 newtons per centimeters, and I want to get a 15 centimeter stretch, so I get a force of 30 newtons. Unless I'm a Ravi, in which case I would have 200, and this would be 0.15, and I'd get 30. How many people got 30? Okay, good. So that's it. That's the nuts and bolts of plugging into F equals kx. Now let's go ahead and use that with our free body diagrams. Because from now on, this is just another force. Remember the forces? Gravity, which is mg. Friction force, which is mu F sub n. Normal force, tension. Well, now we've got another force, kx. So please read example 2 now. So does everyone get a sense that this is what they're talking about? It's a helicopter with a spring attached to the bottom of it and then a mass at the end of a spring? You guys okay with that? Tell me, what am I going to have to get first? K, absolutely. You're kind of dead in the water until you discover what K is, okay? I'm gonna find K and do part A, and then I'm gonna ask you guys to do part B. So here it comes. First of all, we gotta get K.
It's like, oops. 3 divided
So I got F equals KX.
2.8.
I've got a, are you guys okay that 50 kilograms, that's 490 newtons? Okay. So I got a 490 Newton force, and does it 0.8 meters? So I get 612.5 newtons per meter. That's my K. You guys okay with that? And now, I'm going to answer their question. They tell me that the mass, I'm going to accelerate that helicopter and thus the mass upward at 3 meters per second squared. So the next thing I'm going to have to do is make a free body diagram. Here's a free body diagram. There's one force down, and that's the weight of the object. By the way, I'm going to do a free body diagram of the 50 kilogram object. A student earlier today said I could do a free body diagram of the point directly above the 50 kilogram object, and that would be fine too, however you like to think about it. But either way, I've got two forces on that 50 kilogram object, weight down and Kx up. By the way, should I call that negative Kx? That's what Hooke's law says. No, never ever use the negative. I gave you the negative here just to let you know that it's a restoring force, but in every problem you ever do in this class, you'll use positive Kx for the spring force. Okay? And this thing is accelerating upward at 3.0 meters per second squared. I'm going to define up as positive. And now I'm going to do sum of the forces equals ma. I got Kx up, I got mg down, and I got an acceleration of 3.0 meters per second squared. So now I'm going to plug in. My K is 612.5 newtons per meter. Whoa. My displacement, I don't know. My weight is 490 newtons. This is 50 kilograms times 3 meters per second squared. And I solve for x and I get about 1.04. You guys okay with that? Let me give you a second to take that in. And then I'm going to have you guys do part B on your own. Any question or issue on that? Okay, then hey, now your helicopter is accelerating downward at 1.0 meters per second squared. Please get me the stretch of the spring, and I will walk around and help you. Yeah, you're gonna get a right answer.
Mr. Schultz?
Chris's class?
They found
Oh my God. Well, do you have the screws?
Yeah, it's just that the screws, like, if you have them here, like, if you try to put them through, they won't. So, like, if you put the screw like through here, it doesn't like fit through. So, like, I think you just like save them, so, like, you put it through here.
Oh.
Yeah, kind of.
Okay. Do you have like jeweler screwdrivers, the little teeny screwdrivers?
Yeah, I don't know.
Okay.
Yes.
You know what I would recommend? Do you have an optometrist that you go to? Go,
Yeah, I'm going to.
oh, no, just show up
Yeah.
and just tell them, hey, my glasses fell apart, could someone fix them for me? And you don't need an appointment, they'll do it for you, it'll take them 2 minutes. That's what I do all the time. Like if my son used to like to get my glasses, he would take, when he was 2 years old, he would take the glasses off my head and then bandage them. And so they'd get all bent, but I'd have to go to the optometrist and they'd bend them back. And they would do it for me without an appointment. Yes, I see a correct answer. Yeah. Okay. Okay, that should be a negative one. Because you're just already around it. Something's horrible at math. Your math is awful. I'm so sorry, but you're horrible at math. So you'll just have to live your life being horrible at math. Everything you did in physics was good. Yes, that's correct. Good job. Good, I see a correct answer in your future. You're pink. Oh, good. Good. Yay. Oh, I'm in the smart part of the class reading style. So yeah, good for you. Good for you, Justin.
Yeah.
Yay.
Are you ready for your birthday?
Yay. Yay, I see a correct answer in your future if you don't mess it up.
So it's
Oh
in
wait,
November?
just a second. Spring forces, wait, your spring force is up. You're happy it's better.
In second grade?
Yeah, maybe third.
No, don't think of it that way. No matter what direction it's going, gravity's always down and spring force is always up. How would you know? Right. Yeah. Yeah. Good. You're also very clever around here. Good. Great. Really, okay, good.
Oh,
yeah.
yeah.
You're gonna get the right answer. And then this good. Yeah, good. To do your math correctly. Okay, kids. Pretty much everyone I checked got it right. You should get 0.72 meters. So I need to go on to example 3 because I'm running a little bit out of time. I dilly-dallied a little too much. Please read example 3 right now. Okay, so I need to demonstrate for you what they're envisioning is this. I've got a book and I want to hold this book against the wall. And the way I'm going to do it is by exerting a force on a spring. Do you see now, by me compressing this spring, I'm exerting enough force on the book so that the normal force on the book is high enough, so that the friction force is high enough, so that the book doesn't slide down the board. If I let up on the spring, then the book slides down the board. Okay, so here's the next thing I want you to do. Please get me a free body diagram. And I'll give you a hint, there's 4 forces. So give me a free body diagram of that block that's being held against the wall by a spring due to friction force. Okay, here we go. Tell me, give me a force and its direction. Go ahead, Anise.
MG down.
Good, mg down, beautiful. Give me another force and a direction. Yes, Earl.
Friction up.
Good, static friction up. That's what's keeping it in place. And by the way, whenever you see static friction force, you know you're going to end up using mu sub s F sub n. If it's the maximum static friction force, which is this is what it is. Tell me, what's another force? Go ahead, Justin, what's another? Oh, go ahead, Alejandro.
Normal force to the left.
Great. Normal force to the left, because the book is being pressed against the wall, so the wall is going to exert a force back on the book. And tell me, what's the last force?
KX to the right.
Spring force. Yeah. And what am I going to call spring force? Yeah, Kx, always Kx, not negative Kx. Kx. Okay, good. There's my four forces, alrighty? And so I get to do some of the forces in the x direction equals 0, because it's not moving, so there's no acceleration. And some of the forces in the y direction equals 0, because it's not moving. Which should I do first? Go ahead, Logan.
The y direction.
Sure, why the y direction? Okay, well, do I know mg? Sure. Do I know the coefficient of static friction? Sure. So if I do the y's, I can get the normal force. Look at the x's. Do I know the displacement? No, they're asking for it. Do I know the normal force? No. So yeah, we better do the y's first. So I'd like everyone right now to do this. Do the y's first, and then do the x second, and you'll be able to answer their crazy question. Please do that now. I'll define up as positive and to the right as positive. By the way, is anybody here using 10 for G instead of 9.8? That's fine with me. Now, if you want to see if your answer agrees with the book's answer, that is when you're doing these homework problems, then yeah, go ahead and use 9.8. But on my exams and on the AP exam, they're fine with 10, so I'm fine with 10. So if you want to use 10, more power to you. It's up to you. So I get 122.5 newtons. But Gavin, what'd you get?
About that.
125, right?
Yes.
Oh, you're fine with that. You get full credit on my exams. So now let's do the x direction. Kx minus f sub n equals 0. What's the k, 500? Okay. 500 newtons per meter times the x, which we don't know, is going to equal 122.5 newtons, or 125 if you're Gavin. And then I get 122.5 divided by 500. So I get 0.245 meters, or 0.25 meters if you're Gavin. Is that okay with you guys on example 3? That's the level of difficulty you're going to have on tonight's homework. Just a lot of problems where there's another force to deal with, and that's spring force. The last thing I need to teach you about is simple harmonic motion. Do you see that spring mass system? Do you see that mass going up and down? That's simple harmonic motion. If anyone asks you, what's simple harmonic motion? You would say that. You guys okay with that? That's what it is. Notice how it is. Notice the rhythm. Notice how beautiful it is. It's simple, it's harmonic, and it's moving. So we call it simple harmonic motion. Okay. 4 attributes of simple harmonic motion. Number 1, you only get simple harmonic motion when you have a restoring force proportional to displacement. Only happens when a restoring force, so you need a restoring force like a spring, but more than that, it has to be proportional. The force has to be proportional to the displacement. So the big example of that, of course, is Hooke's law, the spring. I got a force that's proportional to a displacement. That means I'm going to get simple harmonic motion. We're going to discover later on the same thing happens with a pendulum, only it's a restoring torque that's proportional to a angular displacement. But for that reason, we get simple harmonic motion with a pendulum as well. Okay, great. Second attribute, the displacement versus time graph is here. I've got this mass going up and down. So it's displacement. At this moment it's there, then the next moment's there, then the next moment's there. Well, if I were to make a graph of its displacement versus time, then I would get a graph that goes along the x-axis. But one way to get that graph would be if I attached a pen. Imagine I attached a pen to this mass and had the pen writing on the whiteboard. So right now the pen is just writing up and down. But what happens if I walk across this classroom like this? What shape would that pen be making now on the whiteboard? What's that?
A wave.
Yeah, do you guys see that? That the pen is going to be making a wave. There's a special name for that type of wave that it makes. You know what it's called? Sine wave, yeah. I used to actually have an apparatus that I described. I had a mass and a spring and a pen attached to the mass. And it kind of worked, but then it broke. A student made it. It was really cool. So I want you to see that the displacement versus time graph is a sine wave. That is, it looks like this. Third attribute. Tell me, during its travels, when is this mass momentarily at rest?
When it reaches the top.
Good. When it reaches the top, and where else?
Bottom. Reaches the bottom.
The bottom. Good. So it's momentarily at rest. Object is momentarily at rest at the extremes. That is, at the top and the bottom, if you've got horizontal, if you've got vertical simple harmonic motion, if I happen to have this on a frictionless table and I put a mass here and I had the mass going back and forth, on this spring horizontally, compression, stretch, then it would be at the extremes, at the maximum compression, maximum stretch. When is this mass going fastest? Is there anybody thinking it's going fastest at the middle? Okay, it's going fastest at the middle. That is, it's going fastest at the equilibrium position. object goes fastest at the equilibrium position. That is the middle. And I have to apologize, I can see I'm running out of time, so I'm gonna have to go really fast. When is the acceleration maximum? Well, I'm just gonna have to give it away. There's a formula relating force and acceleration. That formula is F equals ma. So the acceleration is gonna be maximum when the force is maximum, right? F equals ma. If I want A to be real big, F has to be really big. Well, where in this travels of this guy, or where in the travels of a mass on this spring, when is the force gonna be maximum?
The bottom. Well,
Good. At the bottom, when it's most compressed, or when it's most stretched. At the bottom or the top. The net force, right now at the equilibrium position, what's the net force? 0, it's not moving. Okay, so here, please write this down. When is A max? At extremes, because F is max, and acceleration equals 0 at equilibrium. Sorry about this, because F equals 0 at the equilibrium position. Alrighty, hey, good luck. Remember, when you do tonight's homework, only do positive kx. Restoring force proportional to distance.